This lesson is for Mrs. Cucci's College Now Precalculus class. We are on lesson 4.5, solving exponential equations and logarithmic equations. So if you can get that file open, we'll get started immediately. Okay, so by the end of this lesson, you will be able to solve exponential equations and also solve logarithmic equations. So when we're solving exponential equations, or equations with variables in the exponents, such as 3 to the x equals 20 or 2 to the 5x equals 64, these are what's called our exponential equations. Sometimes, in cases with the equation 2 to the 5x equals 64, we can write each side as a power of that same number. So, in other words, what we're looking to do is try and find common bases. Change that 64 so that it has a base of 2. So we can rewrite it as 2 to the 5x equals 2 to the 6th power. Once we have those bases the same, what we can do is we can then take the exponents and set them equal. So we wind up with 5x equals 6. And then we can very quickly solve for x by dividing both sides by 5, which gives us a solution of x equals 6/5. So in some cases, what we're able to do is we're able to adjust our original equation by finding common bases and then setting our exponents equal to one another and solve. Now, we obviously won't always be able to do this, so there has to be other methods of solving these exponential equations. Okay, so base exponent property, that's what we were just talking about. If you do have those common bases, you can take the exponents and set them equal to one another. All right, so let's try the first one. I have 2 to the 3x minus 7 equals 32. Okay, so what I'm looking to do here is to see if I can find a common base. So we know that 2 can't be written any other way. So we know we're going to leave that portion of our equation. So what we are looking to work with is this 32. Can I write 32 with a base of 2? Well, we know 2 to the 3rd is 8, and then we continue to go up. 2 to the 4th would be 16, and then 2 to the 5th would be 32. So we're going to change that to be 2 to the 5th. Now that I have those common bases, what I can do is I can take those exponents and set them equal to one another to create my equation. And then we solve as I normally would. Add 7, which gives us 3x equals 12. Divide by 3 on both sides, and I get x equals 4. We could also go and use the graphing calculator and solve this graphically. So I'll show you how to do that. I'm just going to insert a graph page, Control-I, add graph. We are going to graph the left-hand side of the equation, which is 2 raised to the 3x minus 7. And we're going to graph the right-hand side of the equation, which was 32. Now, obviously, based on my current window, I can't see the solution, so I do have to adjust the window. If I graph the line y equals 32, we do have to go quite a ways up. So I'm going to hit Menu, Window, Window Settings. My x minimum and my x maximum are okay. My biggest concern here is the y minimum and the y maximum. Since I know I'm going to be rather high up, I don't really need my y minimum to be in the negative values, so I could even make this 10 if I wanted to. But since I want to see the curve, let's make it a -1. My y maximum, I do need it to be larger than 32, so let's make it 40, and then hit OK. Now you can see the clear intersection between the two values. So this intersection right here is the solution to my equation. So how do I get that intersection? We're going to use our intersection tool. Menu, Analyze, Intersection. Lower bound would be on the left-hand side of the intersection. Upper bound would be on the right. And it automatically gives us this point of 432. Since what I'm looking for is my x value, it's going to be my x coordinate, which is important to us, which is the value of 4. So again, I got the same solution whether I did it algebraically or graphically. And also graphing is a nice way to check to make sure that you're correct. Okay, so let's talk about the property of logarithmic equality. The property of logarithmic equality states that for any m greater than 0, and for any n greater than 0, and a greater than 0, and a not equal to 1, I know that's a lot, so just take it piece by piece. M has to be bigger than 0, n has to be bigger than 0, and a has to be bigger than 0. A cannot equal 1. Log base a of m equals log base a of n. If that's true, then we can also say that m is equal to n. Okay, so let's take a peek at 3x equals 20. Now, my first instinct is to take and look and see if I can adjust the base for 20 to be 3. And since I know 3, there isn't any power that I can raise 3 to make 20, I have to have another way to do it. So we're going to use logarithms to do that. Okay, so since I can't adjust, what I'm going to do is I'm going to use logarithms in order to solve this. So what I'm going to do is I'm going to simply take the log of both sides. So log of 3x equals log of 20, using that rule that we just talked about, okay? The base here for these is 10 because they're common logarithms. So now we have to talk about our rules for logarithms. What I know is that if I have an exponent, I am able to rewrite that as a product. So x times log of 3 equals log of 20. And keeping in mind our goal of solving for x, there's just one more step I need to take here. And I can very simply take and get rid of this log of 3 by dividing it to the other side. To get this value here, all I need to do is put it right into my calculator. Log of 20 divided by log of 3. Log of 20, and I don't need to put in the base because the calculator assumes that it's 10 if I don't put anything in. And I get approximately 2.72683. Okay. Now, we could check this by finding 3 to the 27268. And when we do that, and we put that into our calculator, oops, I have the wrong base in there, don't I? I see that it's approximately 20. So that's a nice, quick, easy way for you to check. Now, just like before, we could solve this graphically as well. So we're going to see what that's going to look like. Go ahead and insert a graph page. Just like before, we're going to graph the left-hand side of the equation, 3 to the x. And we're going to graph the right-hand side of the equation, 20. And again, since that 20 is out of my viewing window, I do need to adjust that. We'll make this a -1, 6 perhaps. The maximum, since I had to go to 20, let's say 30. Oh, that's my minimum, isn't it? And here's my graph. So just like before, we're going to go ahead and find the intersection. Menu, Analyze, Intersection, Lower and Upper. and we do find a value of approximately 2.73. You may have more values here. It just depends on what your float setting is set at. I do have mine rather low. Okay, so let's take another one. We're going to solve this one out as well. Okay, so this equation looks a little bit different from the ones that we have been working with. If we're thinking about E and solving these equations, we know we use the inverses to solve these. Just like when we were dealing with this exponential, we used a log to solve it. The inverse of E is a natural log. Right? We know natural log has a base of E. Keeping in mind that our goal is to solve for t, we want to kind of get rid of any of the extra information that's over on that left-hand side. So the first thing that comes to mind for me is this 100. I don't want it there. I want to take it and I want to move it away. And since it's being multiplied, what I'm going to do is I'm going to divide it right over. Okay, so once I have that divided over, now what I'm able to do is I'm able to, just like we did in this example here, take the natural log of both sides. So ln of e to the 0.08t equals ln of 25. Okay, I know the natural log of e is 1. And this comes out front as an exponent, so we wind up with 0.8t equals ln of 25. And then to solve for t, we simply divide. Okay, and when I put this into my calculator, natural log of 25 we get approximately 40.2. Okay. And as we did before, we can also solve this graphically by graphing that left-hand side and the right-hand side. So you can do that on your own if you'd like to take a look and see what that looks like. Okay, so let's try another exponential equation here. I have 4 raised to the x plus 3 equals 3 raised to the negative x. Okay, so since we're dealing with a nice exponential function or exponential equation here, what I'm going to do is I'm going to use the logarithm again. Now I'm not going to use natural log because I'm not dealing with a base of e. We're going to use just a common log. So log of 4 raised to the x plus 3 equals log of 3 raised to the negative x. Okay, so what I'm going to do next is I'm going to go ahead and I'm going to rewrite this by moving my exponents. So these exponents come out front. X plus 3 log of 4 equals negative x log of 3. All right, one of the ways that I am able to rewrite this is by taking this x plus 3 and breaking it up into 2. So I could say x log 4 plus 3 log 4. I know we haven't seen that done before, but that is another way that I can do it. It's simply removing parentheses. Okay. So now what I'm going to do is I'm going to move some things around. I kind of want to get these x's on the same side. So what I'm going to do is I'm going to move this to the right-hand side, and I'm going to move this to the left. So x log 4 plus x log 3 equals, moving this over, negative 3 log 4. Now I notice I have x's on this side, 2 of them, so what I'm going to do is I'm going to take that out as a GCF, because again, our goal is to get down to 1x and to get it alone. So this will allow us to achieve that. So now to get that x by itself, what I'm going to do is I'm going to divide both sides by log of 4 plus log of 3. And to find this value, I simply plug into my calculator. Okay. And when I do, I get approximately negative 1.6737. Okay, so I do want to look at the graphical solving method for this one because it does look quite a bit different. Because what we're doing is we're setting two exponential equations equal to one another. So, or exponential expressions. 4 raised to the x plus 3. Exponential functions, I'm sorry. I keep getting my words jumbled on me this evening. And 3 raised to the negative x. Oops. And I'm just going to take this and pull it down. I see that intersection right there. That is where my solution is. So again, menu, analyze, intersections, left and right. And there's my solution again, approximately negative 1.67. So again, you can do it algebraically and graphically, either way you choose. All right, so we're going to do one more of these, and then we're going to call it a night. All right, so I have e to the x plus e to the negative x minus 6 equals 0. Okay, so the first thing that comes to mind for me is this negative exponent. I don't like negative exponents per se, so I want to make it so that it's not negative anymore. And we know in order to get rid of a negative exponent, I simply need to take it and put it under 1. Okay, so what I can do next, because now I don't like this piece, is I can take it and I can multiply both sides by e to the x to kind of clear that fraction. Okay. E to the x times e to the x is e to the 2x. When I multiply variables, I add their exponents. E to the x times 1 over e to the x is 1. And minus 6e to the x. And 0 times anything is 0. Okay. I don't like the way it's set up, so I'm just going to rewrite it so that it's in a nice descending order. Now, when I look at that, the first thing I think of is factoring. Unfortunately, there's no two numbers that multiply to be 1 that will add to be a negative 6. So what I have to use is actually the quadratic formula. Okay? But in order to use the quadratic formula, we need to do something called a u substitution. So what I'm going to do is I'm going to say we're going to let e to the x be u. So I'm able to rewrite this as u squared minus 6u plus 1 equals 0. Which is prettier to look at. We're more used to seeing things that look like that. But it's still not factorable. So what I have to do is I have to go through and I have to use quadratic formula. So that x equals negative b plus or minus the square root of b squared minus 4c all over 2a. That nice little song that we have, except instead of solving for x, we're solving for u. So u equals negative b plus or minus the square root of b squared, so 36, minus 4 times 1 times 1, ac, all over 2a, or 6 plus or minus 36 minus 4, which is 32, square root of 32 over 2. I know that the square root of 32 reduces. 16 and 2, so 4 square roots of 2 over 2. Right, square root of 16, square root of 2, that's where I got that from. And this reduces just a little bit further to be 3 plus or minus 2 radical 2. Okay, so what equals 3 plus or minus square root of 2 square root of 2 is u. Remember, I let e to the x equal u. So I need to rewrite this as e to the x equals 3 plus or minus 2 radical 2. Okay? So what I need to do is I need to now solve for this x. And we know when we're solving exponential equations with a base of e, we use the natural log. Okay? So we get x equals natural log of 3 plus or minus 2 radical 2. Now, remember, this is two solutions. We have to put it in separately. ln of 3 plus 2 radical 2 and ln of 3 minus 2 radical 2. When I put these into my calculator, I get approximately 1.76 and negative 1.76. And there's your solution. Okay, I did go over by a minute. I apologize. Thank you guys for hanging in there with me. And again, if you have any questions, make sure you mark down the time at which you had the questions and come in prepared to ask those questions tomorrow. All right, thank you guys. Bye-bye.